Okay guys, we're going to go over quiz 13J. This is the material we are getting ready to go over in quant after spring break. So you'll have plenty of time to look over this and let it sink in and make sense. I want to get these videos done and up as I'm going out of town for a science convention. So I want to get a couple of these done for you guys before I go. So let's take a look at this. We have got a 45 milliliter aqueous sample of a monoprotic weak acid. And then it's got our molar mass here, so we're going to do something with that at some point. It's titrated to the equivalence point with 40.11 milliliters of 0.1067 molar sodium hydroxide. So this is a strong base. So we've got a weak acid here, and we've got a strong base. And what that is going to tell us is that our pH at our equivalence point is not going to be 7. This is not going to be a neutral solution. And it gives us the Ka of Hc. So we're going to have to do something with that at this point, I'm sure, in this thing too. So first question, what is the molar concentration of Hc in the diluted solution? Now, one thing that I have noticed with Dr. Butcher is that he will use this phrase, molar concentration, to mean a couple of different things. He will mean how many moles is it, or he will mean what is the molarity. And sometimes you have to figure out which one he's actually looking for. In this one, he's looking for molarity. And he's given us the information to find it because we've got our volumes and molarity for equilibrium of our base, and we've got the volume of our sample. So then we've got to find the molarity, okay? So we're going to set this up the same way we did before. Our equation is going to be molarity of our acid times the volume of our acid divided by Na. So remember, N is your stoichiometric coefficient in a balanced chemical reaction. And then we're going to set that equal to Mb Vb over Nb. Now, he does not give us an actual chemical equation on this, but we are going to assume that they are of 1-to-1 ratio. If they weren't going to be 1-to-1 ratio, I'm sure he would have told us that they were not 1-to-1. And we are going to solve for the molarity right here. All right, so let's sub in our numbers and let's get started. So we've got 45 milliliters. And then we've got the molarity of our acid. This is what we don't know. And then we're going to set that equal to 41.1. And we're going to divide both sides because we got to get the molarity of the acid on its own by 45. And that is going to give us the molarity of our acid is going to equal, my calculator just shut off, 0.0951, 0.05, so 1. Molarity of our acid is there. Okay, so question B, what is the total mass of Hc, remember this is our weak acid, in grams in the sample? So we have our molarity here, and we have our volume. So now we have to find moles. That is step 1. So we've got 0.09511 moles per liter. And we're going to multiply that by our volume in liters. And those units will cancel. And this will give us just moles. Right. So now we have 0.00428 moles. All right. But we're not done yet because we have to go from moles to grams, right? So 1 mole, and he gives us our conversion factor here, is 98.52 grams. And then we're going to do that conversion. And that is going to give us 0.422 grams. Okay. So, part 3, what is the pH of the solution before the addition of any sodium hydroxide? Now, this is where the Ka is going to come in. Remember up here we got our Ka value. We're going to remember that Ka is going to equal, let's actually write down our equation first. This is the easiest way to do it. So before any of our sodium hydroxide, all we've got is Hz. And it's going to dissociate into H plus and Z minus. Okay, so our Ka is going to be H plus Z minus over Hz. We do have our Ka value. We do have our Hz value. Okay, this is our molarity number that we came up with earlier. All right, guys, I am going to apologize for my voice. It seems like my voice is starting to go a little bit. But we're going to remember that at equilibrium, where we have our Ka value, our H plus and our Z minus are the same. So we're going to represent that with X, because there's 2 of them. It's going to be squared over Hz. And so we have to find the value of X. So we're going to isolate that. And X is going to be equal to the square root of Ka times Hz. All right, let's get some numbers put in there. Our Ka is 2.5 times 10 to the negative 7. And we're going to multiply that by our molarity of our Ha, which is here. All right, I'm going to pause this and run that through the calculator. Okay, and that's going to give us an X value equal to 1.54. And we're going to remember that that is equal to our hydrogen ion concentration, and we're going to plug that into our pH formula. And that's going to give us a pH of 3.81. So really, we're just taking what we've learned in previous sections and we're combining it together. Now, here's where things get a little bit different, because we need to know what the pH is at the equivalence point. Because if you'll remember, we've got a weak acid and a strong base, and it is not going to be 7. Okay? All right, so we're going to revisit our equation here just a little bit. So we've got Hz plus NaOH. Okay, and then this is going to go, we're going to have our water. We're going to have Na plus, which this is a spectator, it ain't going to do nothing. Then we're going to have water. And then we're going to have Z minus. Okay. Z minus is where our pH is going to come from, right? Because that is our conjugate base. Now at equilibrium, we have got equal amounts of our H plus that comes from this and our OH minus that comes from this one. But we still have our Z minus, okay? So that's what we're going to be trying to find, is this guy right here. So our first step is we've got to figure out the molarity of our Z minus. Okay, and so we're going to start with the molarity of our HC. Okay, and that was the molarity of our weak acid. Okay, it's going to be 0.09511 times our volume, okay, which if you look up here in our original problem, that was 45 milliliters. Okay. and we are going to take this total and we're going to divide it by the total volume of our solution. Okay, so that is 45 milliliters, right, of our acid plus 40.11 milliliters of our base. Okay, and then when we do that, we're going to be dividing by, and this is in milliliters, right? So this is going to be 85.11 milliliters. And the milliliter and the milliliter are going to cancel out, and so that's just going to give us molarity, right? 0.0503. It's 0.28, but I'm going to round up a little bit. Or, well, 0.29. We'll do that way. We'll give it an extra significant figure just for giggles. Now, our next step. So we know that this is the molarity of our Z minus, right? But now we need to find Kb because we've got to find pH. And in order to find pH, we have to know our Kb. Now, we have our Ka of Hz, and we know what the Kw is for water. So we're going to set our Kb equal to Kw divided by Ka. Okay, so that's 1 times 10 to the negative 14 divided by 2.5 times 10 to the negative 7. That's going to give us our Kb. All right, and that's going to give us 4.0 times 10 to the negative 8. And now we're going to take that and we're going to plug that into our formula for Kb. So Kb, and let's just write up our formula here for the dissociation of this with water. So Z minus plus H2O is going to give us HC plus OH negative. Okay, so Kb is going to give us HC OH minus over our Z minus there. We're going to sub those in for X, so X squared over Z, and we're going to start filling in some numbers. Right, so we have our molarity of Z. Let's isolate our X. And the way that we're going to do that is we're going to do X is equal to the square root of Kb times the molarity of Z minus. Okay. I'm going to fill in the numbers here. Zero 0.05029, and that is going to give us X equal to, X is going to be equal to 4. Well, it says 4.8, but he's really wanted two significant figures, so we're going to say 4.4 or 4.5 times 10 to the negative 5. Now remember, this is OH minus, so we're going to be plugging this into POH. And so we're going to take the negative log of our answer there. It's going to give us a POH of 4.348. And then we're going to subtract that from 14. And that is going to give us a pH of 9.65. Okay, so this is not anything that we really haven't covered before. It's just combining things in a different way. If you have any questions or if you need anything broken down a little bit more, don't hesitate to email me or drop it in the comments. I hope you guys have a great break, and I'll see you guys in a week.